All right, picking up where I left off, we're analyzing a multi-loop circuit, and I pointed out that not only does Kirchoffs' first loop rule apply to this, that our net change of potential as you traverse a closed circuit loop within the circuit, that sum of changes of potential has to be equal to 0. We also discovered a second loop rule, which is that when a current goes into a branch, that is to say a second subpart of a circuit, that some of the current will go take one path, the rest of the current will take the other path, and conservation of charge demands that the total amount of charge that comes out of that branch must be equal to the total amount of current that went into the branch. Kirchoffs' first loop rule, I said, and I'll repeat here, is a statement of conservation of energy. Kirchoffs' second loop rule is a statement of conservation of charge. And yes, I will care deeply about that on tests. All right, so there's that. Now, there's a couple of statements that I want to make to clarify some things, add some detail here. First of all, Kirchoffs' second loop rule does not say that the current that comes out of a branch point must be equal to the total current or the maximum current that flows in the entire circuit. That's not true at all. That happens to be true in this case, but that's only because this particular circuit, simple as it is, only has two subpaths, right? And but it would not be at all difficult to construct or even imagine a circuit that has 3 or 4 or 5 or 10,000 sub-branches. Okay, and so Kirchoffs' loop rule does not, second loop rule doesn't say that the total current comes out of every branch, only that whatever went into that branch comes out of that branch. So there's that. The other thing I wanted to mention is this diagram that I've made here, specifically the little arrowheads that I put on there to indicate the direction of current flow, is entirely arbitrary in the sense that I don't actually know ahead of time, absent any numbers, what direction the current is going to in fact flow, not only in the circuit as a whole, but in either of the individual branches. Okay, and so what will happen is that when you do your algebra, and then if you end up having numeric values that you plug in, it's entirely possible when you calculate the current in one, let me back up a step. The goal here is going to be to calculate not only the total current that comes out of, let's say, this battery over here in this example, but also calculate the current in each of the sub-branches. So in this example, not only do I want to calculate the total current I also want to calculate I1 and also I2. And the way we usually say that, how much current flows through resistor number 1, how much current flows through resistor number 2. So that's what we're going to be solving for, is I1 and I2. Once we have I1 and I2, calculating I is of course trivial. But what I wanted to say was that if you plug in actual numbers and calculate these various currents, the result of doing your algebra may well be that you get a negative number for one or more of the subcurrents, and that's fine. All that means, if you do get a negative current, all that means is that the current flows in reality in the opposite direction from the direction you chose when you set up your equations. So that's something to be aware of. You almost never know a priori what direction the current is going to flow in any of the particular branches. And in fact, there's a subtlety involved in thinking about the directions that probably best to discuss it in class, or I might make a separate recording on it, but probably we'll discuss it in class. Anyway, so let's tackle that. So given this problem, I'm going to choose some actual numeric values for this, and let's actually do it. Let's calculate I1, I2, and the total current I that flows. Okay. What we will do is apply Kirchoffs. We'll start out by applying Kirchoffs' first loop rule to our diagram here. And then, having done that, anytime we encounter a branch point, we'll apply the second loop rule. So it's going to go like this. we have two unknowns, I1 and I2. I by itself is trivial, right? So the two unknowns are I1 and I2. That means we need two equations and two unknowns. We will get the equations that we need by applying Kirchoffs' first loop rule. We will recognize that we can get two equations by applying Kirchoffs' second loop rule. So here's what you do. You choose, there's several possible circuit paths that the current can take. For purposes of calculation, you choose any two independent circuit paths. And I mean algebraically independent, not physically independent. And you write down Kirchoffs' first loop rule for each of your subcurrents, sub-branches, and that gives you two equations, and you solve the system simultaneously. Here's an example. I'm going to start at point A. I'm going to traverse a closed path around the circuit, writing down the changes of potential that happen all the way, and then set that sum equal to 0. And so, and I'll do that twice, once for two different circuit paths. So we'll start at point A, and I'm going to just sort of arbitrarily choose the path outside this what I guess refer to the outer path. So I'm going to start at point A. We're going to go across V1. We're going to gain potential in crossing V1, going from low potential to high potential, and then I1. Now, the thing is, as we make our way around the circuit, at this point, the circuit branches, the circuit splits. And so I'm going to the outer loop, but the next thing I encounter in the outer loop is resistor number 2, but the current that is flowing through resistor number 2 is current I2, not the total current. And that's the key here. And so we'll write down the change of potential as the current I2 flows through this resistor. And then we'll calculate the change of potential here. This is going to be a loss of potential because we're going from high potential down to low potential. And then we'll come back around here. And then when we return to this branch point, now the currents have rejoined, and so the current that flows through resistor number 3 is the total current once again. So that's the trick and the issue of doing Kirchoffs' first loop rule with a multi-branched circuit. So let's start with that. So we'll write down the equation by analyzing the outer loop. It'll be our first equation of the two that we need to solve for I1 and for I2. Okay. So starting at point A, we go up V1, so we gain some potential. And then the next electric device that we encounter is resistor R2, but the current that flows through resistor R2 is current I2. So this right here, I2 times R2, that's just Ohm's law, V equals IR, remember? Okay? And then the current flows through V2. There's a loss of potential, as I described a moment ago, so minus V2. And then the next thing we encounter is this resistor here. Again, the total resistance is flowing through resistor number 3. And so just I now, no subscript, times R3. And then we're back to our starting point, not encountering anything else. And so that's the end of the changes of potential, and those have to end up summing to 0. Okay. And I can anticipate what's going to happen next by realizing that the current, capital I without any subscripts, is simply, or can be trivially rewritten as I1 plus I2. 1 minus V2 minus I2 R2 minus I1 plus I2 R3 equal to 0. Okay? And we could do more algebraic fiddling around, but there's not a whole lot of value to it, not at this point anyway. So this is our first equation of the two that we need in order to solve for two unknown currents. Okay, so that's equation 1. For equation 2, we'll choose one of the other loops. It does not matter which one. And I think I will choose the left loop here. So once again, I'll start at point A, and I will make my way around, but this time I'm going to make my way around only the left loop here. Okay. I could have chosen the right-hand loop. I don't want to choose the right-hand loop because there's a subtlety involved in there that I don't want to talk about right now. I'd rather talk about it in class. So let's just leave it at the left-hand loop. So we start at point A once again. So left loop. So we gain V1, and then we're taking the left-hand loop, right? So the next thing we encounter in this path is resistor R1, but the current that flows through resistor R1 is now just current I1. So we have minus I1 R1. And then the next thing we encounter is R3, once again, the total current, and I'll go ahead and short circuit to that. I'll immediately substitute for the current capital I, and then we're back to our starting point. And that's that. And that is our second equation. And the rest, of course, is more or less trivial algebra. So we want to solve for I1 and I2, and then it's just solving two equations and two unknowns. I'll leave you to do that algebra. I'm going to pause the recording, however, and what I'm going to do is, because let me be more honest with you than perhaps is necessary. In the example that I have, I originally did this example with numbers to start with, and I want to, and I'm going to show you that. Might as well, once in a while do an example with numbers. That's not bad. Okay. But I want to give you the algebraic solution, so I'm going to let you do the work. I will tell you what the solution is here on the screen, but I had just decided while I was actually in the middle of this recording not to put in the numbers, so I don't actually have the algebraic solution handy. But I'm going to pause the recording. While the recording is paused, I'm going to create a Sage worksheet and have Sage do the algebra for me because I don't feel like doing it. And when I restart the recording, I'll have the solution and I'll write it down for you so that you can check your work. All right, as promised, here are the solutions that I came up with using computer algebra software. Much faster than trying to, much faster and much more accurate than trying to do it by hand. So you can take a look at this. A couple of things I want to point out about the algebraic solution. A skill you need to develop, by the way, is to be able to look at the algebraic form of a solution and interpret it both physically and mathematically. Does it make sense? To start off with, let's just check out the units. We're calculating current, so we expect the units to be amps in the SI system. V times R, clearly those aren't units of amperes. But if you look at the denominator is units of R squared. R1 times R2, I'm sorry, the units are ohms squared, square ohms. So the resistance in the numerator, R to the first power, R to the second power in the denominator. So we end up with units of potential in the numerator divided by R to the first power in the denominator. In other words, V divided by R, which of course is amperes, from Ohm's law. So volts divided by ohms is amps. So that works. And the other thing you'll notice is different from the previous example where I had just a single loop circuit, and in that one I simply had V on the top, no resistance, no resistors, no R's in the numerator in the earlier example when I only had one single loop. I had V in the numerator, I had R equivalent in the denominator, and that was it. The reason, but here I've got resistors both in the numerator as well as in the denominator. The reason for that is, perhaps you notice, perhaps you realize, is that in the first example with just a single loop, all the resistors were in series. And so you just get the equivalent resistance by adding the resistances together. But here, I've got two resistors in parallel, and both of these parallel resistors are in turn in series with this resistor. So we've got both series and parallel happening together, right? And so you would expect that the reciprocal relationship for parallel resistors would come into play, and it does, and that's the reason in this algebraic solution that I have resistance in both the numerator as well as in the denominator. Okay, so there's that. So you spend some cycles staring at that and making yourself happy with that. Now, I'm going to redo the same problem, but this time I'm going to solve it with numbers from the get-go rather than with algebraic symbols. And there's no reason to erase that. So the only thing that's going to happen differently here is that when I write down the equations, I'm going to write down using numbers directly. Now, you know, you've been watching me long enough to know that I don't normally like to do that. Normally, I substitute numbers at the very end. But there's some useful ideas that come up when you start with the numbers much earlier in the solution process. So I want to show those to you. Obviously, I could simply take these solutions here and plug in the given numbers, and you should do that. But I'm going to do something a little different here. I'm still going to use the same loops. My goal is the same, is to calculate both currents. But let's do it with numbers. So let's suppose that, let's see. Suppose V1 is that battery provides a potential of 12 volts, and V2 will be 5 volts. R1 will be 4 ohms. R2 will be 2 ohms. These numbers are just made up. And then R3 will be 3 ohms. Once again, I'm going to write down the equations that you obtain from applying Kirchoffs' first loop rule, keeping in mind that we have to worry about branching in the second loop rules, from the second loop rule. Okay. And, okay, so once again, we'll do the outer loop, start at the battery. But, so I'm going to gain 12 volts. And then outer loop I2, we don't know what I2 is. That's one of the things we're solving for. It goes through the resistor R2, which is 2 ohms, and it's going to lose potential. So I2 times 2 ohms. And then we're going to lose potential, V2, minus 5 volts. And then our total current, which is I1 plus I2, is going to go through R3, which is 3 ohms. So we're going to lose that. So minus I1 plus I2 times 3 ohms. And we're back where we started, and that's equal to 0. Meanwhile, so that's our first equation. And then I'll skip to our second equation. So we'll go to the left-hand loop here. So once again, we start at point A, go across the first battery, so we gain 12 volts. Then we're going to go, the next thing we do is current I1 through this resistor here. This first resistor is 4 ohms, so we have minus I1 times 4 ohms. And then branch point here, the currents recombine. Kirchoffs second loop rule says the total current through R3 has to be the sum of both of them. So that's a loss of I1 plus I2 times R3, 3 ohms. We're back at point A, and there we are. Okay, let's clear things out a little bit. First of all, 12 volts minus 5 volts, so that's 7 volts. Okay, and then we have, well, I'll just leave that, minus I2 2 ohms. Like that, clear these parentheses, so we have minus I1 3 ohms minus I2 3 ohms is equal to 0, right? I2 times 2 ohms, I2 times 3 ohms, minus, so those add. So we have 7 volts minus 5 ohms times I2 minus 3 ohms times I1 is equal to 0. You'll notice that I rearranged the numeric value. And the reason is now I'm going to pull a clever trick. Okay, and that is I am going to divide both sides of this equation by by 1 ohm, or multiply both sides of the equation by 1 ohm. Why in the world am I doing such an odd thing? Well, let's look at it. First of all, dividing by 1 over ohms, that cancels out that unit and that unit. So there's hooray for that. Okay. And now I can move over here, move the camera over here. And the second thing is a volt divided by an ohm is an ampere, is an amp. Okay. And so that means in turn that I can write this as, I have to redo this because I need the room. So this becomes 7 amps minus 5 I2 unitless, or at least this the coefficient is unitless, minus 3 I1 is equal to 0. That's unchanged, of course. And the reason, and so why did I do this? For 2 reasons. The primary reason is it just makes the equation look much simpler. And the second reason I did it is keeping in mind that what we are ultimately solving for is a couple of currents. Currents have units of amperes, and so this just kind of cleans that up in terms of the appropriate units. So the trick that I wanted to show you was primarily this, was the dividing by 1 ohm to clean up your units. Apply the same strategy to the left loop. I'll just rewrite that. I'll rewrite the left. Funny. Okay, so once again, left-hand loop was gain 12 volts, lose I1 times R1. R1 is 4 ohms. And then lose the potential through resistor number 3, which is 3 ohms. Those sum to 0. And now again, I'll do the same algebra. So 12 volts, that's the only one there. So 12 volts minus, let's see, yeah, I'll just leave that, minus 4 ohms I1, minus 3 ohms times I1, minus 3 ohms times I2. That's equal to 0. So we have minus 4 ohms I1 minus 3 ohms, so that's minus 7, so we have 12 volts, minus 7 ohms, I1, minus 3 ohms, I2 is equal to 0. And same trick as before, multiply by 1 over ohm on both sides. And that gives us equation number 2, then in its simplified form. Had my back to the camera all this time, sorry about that. Okay, so 12 volts divided by 1 ohm is 12 amps. And then these units cancel here. So we're left with minus 7I1 minus 3I2 is equal to 0. And that's our second equation. Right. And there's our system of 2 equations and 2 unknowns. Solving. You should check this. You should do the math yourself and convince yourself that you get I1 is equal to 1.5 amps. I2 is equal to 0.5 amps. And that's the answer. Okay. 2 final comments. To start with, as I mentioned before, once you have specific numeric values for the various quantities, it's possible that you might end up with a current that has a negative number. If you do, all that means, as I said earlier, is that the current with the negative value flows in the direction opposite the direction that you assumed when you set up your equations. So in particular, in this drawing here, I drew my arrows all these ways. Had I gotten a negative value for, let's say, I2, which is the 0.50, then that would have meant that the current was actually in this branch out here was actually flowing the opposite direction. Now, of course, all the other currents have to be consistent with that. So, yeah, don't worry about it. There's if you get a negative current, that does not necessarily mean that anything went wrong, but you should check your work anyway. The other thing that I wanted to mention was, my mind is blanking. I'm going to pause the recording until I remember. Right, sorry, yes, now I remember. Now that we've gotten the values for the currents in each part, depending on what you've learned up to this point and stuff, we can now calculate the power through each resistor through I squared R or V times I. We calculate the potential drop across each individual resistor, things like that. In fact, that seems like a pretty good example to do in yet another recording. So one more recording I think should do it. We'll do some examples of taking these values and solving for other things.